So chapter 3 is all about exponential functions and logarithmic functions. Maybe that rings a bell. Maybe that makes you excited. Maybe that makes you not excited. I don't know. But that's what we're dealing with. Okay? So last chapter we worked with polynomials, where we had x and that was raised to a power. Now we're going to have a number raised to a power, and our variable is now in the power. Okay, so that's what makes it an exponential function, is now our variable is in the power. Okay, does anybody remember what these graphs look like? I think you're thinking about it. Okay, so if something is growing exponentially, how would you describe that? It gets bigger and bigger and bigger each time, right? And bigger by a lot. Here is an exponential graph. I'll highlight it. Okay, what's that dotted line there? What's that called? It is the x-axis. It's called an asymptote, right? Okay, we have an asymptote here at y equals 0. Let's talk about y. Okay, first of all, what's the domain of this graph? Thank you, all real numbers. Okay, what about the range? Okay, let's talk about why the range is 0 to infinity. Okay, this is a graph of a number raised to the power of x. Can I take a number and raise it to a power and get a negative value? Can I take, let's say 2. Can I raise 2 to a power and get a negative number? No, because even if we have negative exponents, right? Like 2 to the negative 2, that just means 1/4. Okay, so we cannot take a number, raise it to a power, and get a negative value. So that's why our range is 0 to infinity. We're not going to have negative numbers. Okay, where is this function increasing? Where are we increasing here? From left to right, where are we rising? Thank you. Are we ever decreasing? No, because we have exponential growth. It grows over the course of the domain. It just gets bigger and bigger and bigger from left to right. Okay? Our y-intercept is going to be at 0, 1. Why would that be the y-intercept? When you take a number to the 0 power, what do you get? 1 every single time. Okay, so our y-intercept is 1. Okay, so this we would describe as exponential growth. What happens when we have a negative x as our exponent? This is no longer exponential growth, but exponential decay. Right? You talk about this a little bit in science, yes? No? Maybe? Yeah. What science class, Courtney? Biology. Okay, so what's our domain for this one? Real numbers. Our range. still 0 to infinity. We can't take a number to an exponent and get a negative value. Okay? Are we increasing? No, exponential decay. We are always decreasing. And here again, our y-intercept is 0, 1. If I take a number and raise it to the 0 power, it's always going to be 1. Okay? We once again have that horizontal asymptote at y equals 0. Okay? For any exponential function, if we're talking about the parent function, okay, we haven't shifted it or anything, we're going to have a horizontal asymptote at y equals 0. Can we take a number and raise it to a power to get 0? We can't, can we? We cannot take 2 and raise it to a power to get 0. We also cannot take 2 to a power and get a negative value. So we have that horizontal asymptote that our curve is going to be approaching, whether we're growing or decaying. We're going to approach that asymptote because we cannot take a number to a power to get a 0. We cannot take a number to a power to get negatives. Okay, so we approach that asymptote to reflect all of those values. Okay, so a part of your homework is going to be graphing these. You graphed these last year. Let me tell you what my expectations are. Okay, so I want you to graph 3 to the x power. Does anybody remember what their instructions were to graph these last year? Okay. This is a parent function, right? There aren't any shifts. Okay. So we have a horizontal asymptote where? Y equals 0. Okay. I want you to pick 3 values. -1, 0, 1. What do you get when you plug in -1? Thank you. So we have the point -1, 1/3. What about when we plug in 0? 1. And what about when we plug in 1? 3. If you want more points, go for it. But this would be the minimum. Okay? This is something that you're graphing without a calculator for me on Friday. So make sure you practice these without your calculator. Okay? Now, let's very quickly review our transformations. What does A do to our graph? Okay, so we can do a stretch or a shrink here, right? What about if it's negative? If we have a negative A, what does that do to our graph? Good. Reflects it about what? Good. Yeah, x-axis. You were thinking it correctly. Okay. What about H? What does H do? It's inside, so it's going to be the right or left shifts. But Michaela, K would be up or down shifts. Okay? I know you thought that you were done with these in chapter 1, but you will never be done with transformations, ever. Okay? They're going to come up all year. All right? So now, let's talk about graphing with a transformation. Okay? This is the graph. What would the parent function be? Okay, where A is 3. So our parent function is 3 to the x. That is what we just graphed. And g of x is 3 to the x, and then what happens to it? Okay, so this is shifted left 1. Okay, so we know that our parent function has these values. So if we're going to shift those to the left 1, okay, -1, 1/3 becomes -2, 1/3. 0, 1 becomes -1, 1. And 1, 3 becomes 0, 3. Did our horizontal asymptote move at all? No, it gets to stay. And then there's our graph. Okay, so here would be the points that I want to see. If you want to make a table of your parent function, you can. If you want to think about them in your head while you're shifting them and then write these points down, that is fine. But I want you to think about the -1, 0, and 1 x coordinates of the parent function and then shift them. Okay? Because if we have a couple different shifts going on, -1, 0, and 1 might not be the points you want to plug into your shifted function. Always plug those into the parent function and then shift them whatever which way. Okay? What is the domain of this function? Thank you. All real numbers. What about the range? Okay, 0 to infinity. We had that horizontal shift, but it did not affect our domain or range. Let's talk about this graph. Our parent function is still 3 to the x. However, from our parent function, 3 to the x, how does this look different? Shifted down 2. So this is a shift down 2. So our parent function, 3 to the x, we know that we have these points, right? We graphed it already. So now what we're going to do to graph 3 to the x minus 2, we're going to take these points. So the -1, 1/3, when we shift that down 2, we have, what do we have? -1 and then -1 2/3. We shift it down 2. Right. Our parent function has the point 0, 1. It becomes the point 0, -1. And then our parent function has the point 1, 3. If we shift it down 2, it becomes the coordinate 1, 1. I just took those 3 coordinates and shifted them down 2. Is our horizontal asymptote still y equals 0? No, Grant, you're shaking your head. Where is it? Okay, it also gets shifted down 2. So down 2 for our horizontal asymptote means it's at y equals -2. And here is our graph. You must include your horizontal asymptote on your graph. If you do not graph the horizontal asymptote with your curve, you will not get full credit for your graph. All right, one more. Negative 3 to the x. If our parent function is 3 to the x, what is that negative doing to each of those coordinates? What's that negative doing? Reflecting over the x-axis. So negative 1 1/3 becomes negative 1 negative 1/3. 0 1 becomes 0 negative 1. And 1 3 becomes 1 negative 3. Where's our horizontal asymptote? Thank you. Y equals 0. When is the only time our horizontal asymptote is going to change? If we have a vertical shift of some kind, if our graph has been shifted up or down, our horizontal asymptote is going to change. Now, I want to go back to this previous example that we did where our horizontal asymptote is at y equals negative 2. Okay? We forgot to talk about domain and range for this example. So go back to the previous example. What's the domain for 3 to the x minus 2? Okay. What would the range be, though? Negative 2 to infinity, because that horizontal asymptote got shifted down too. Awesome. Okay. Okay, let's just practice some transformations, just describing them. That way when you get to your homework, you will not have a problem. So 4 to the x would be our parent function. 4 to the x minus 2, how would that look different? Okay, this is shifted right 2 from our parent function. So if you were to graph this, you would think of the coordinates, negative 1, 0, 1, here at 4 to the x, and then shift them all to the right 2. What about this one? Okay, there's two different things. Okay, so this is an up 3, but before we do the shift of up 3, what does this negative here do? Okay, so we have a reflection over the y-axis, and then shifted up 3 from 4 to the x. Okay, so here again, think of those 3 coordinates for 4 to the x, flip them over the y-axis, and then shift them up 3 to get your new table of values. Okay, I need to see those 3 points at least for your graph that you're graphing, okay? Some of us can think of those 3 points for the parent function in our head, that's fine, but make sure you have a table of values with those 3 points for whatever you're graphing. Okay? All right. Let's talk about the number E. E is what we call Euler's constant. Okay? And it is known as the natural base. Okay? He is probably one of the more important bases in exponential functions. And E will also be an important base when we talk about logarithms tomorrow. Okay? It is an irrational number and can be approximated to 2.718, blah, 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 blah. Okay? But it's an irrational number, much like pi. Okay? Yeah. I could take you in this big, long proof of what the number e is, if that's something that interests you. I don't even think our book talks about it. That's pretty disappointing. There's actually this big long formula explaining what the number e is. Did your teachers last year show you? If you can even remember. Okay. Well, maybe if we have time on Thursday, I'll pull it up. Or maybe not. Okay. But there's this big long proof of what e is. Okay. So let's talk about the graph of e to the x. Okay, is it going to look much different? The graph of e to the x, is e still a number? Raised to the x power. Okay, so are we going to have a horizontal asymptote? Yes, Mrs. Holman, we are at y equals 0. Okay, get out your calculator and find your e button. What's the y-intercept without punching it into your calculator? What's e to the 0? 1. Okay. Go ahead and find e on your calculator and take e to the first power. E to the first power is 2.71, blah, blah, blah. Great. Now find e to the negative first power. And what do we get?
Syntax error.
Are you using a negative sign? I'm putting it in a yeah, it's going to be the negative sign. All right, what did you get?
0.3678.
Okay, so kind of around it. All right, there is our e to the x power. It looks the same as all the other exponential functions, okay? But e is an irrational number, so our values aren't extremely beautiful points. All right, what can we do with this number e? You have a couple formulas you talked about last year with the number e. You remember? Compound interest. Okay, why is interest important? Okay, bank accounts, savings accounts, loans, like maybe a car loan or a house loan. You know, things like this. Probably more, house loans are a little different. Probably more like a car loan. Okay? So if you do not have enough money to buy a car, you loan the money. However, as you pay it back, you don't just pay the amount that you borrowed, you pay the amount with interest. Okay? The longer you take to pay off your loan, the more interest you have to pay. Okay, so this is compound interest, where you start with a principal amount, and the interest is compounded or calculated every so many times a year. Okay, so this would probably be more of a savings account example if your interest is calculated every month. Then that would be 12 times a year. Every week, that would be 52 times a year, right? You have a rate at which your interest is calculated. Your rate has to be a decimal, and time is going to be in years. Now, we can calculate interest every so many times per year, or we can calculate it continuously. This may be the formula that you are familiar with, PERT, right? Where we still have a principal amount, we still have a rate over so many years. However, our interest is being calculated continuously. Okay, so this would probably be more of like a car loan example. All right. So to decide what formula you need to use, you need to figure out, am I compounded so many times per year or continuously? But then everything else is similar as far as the rate needs to be a decimal. Time more often than not is in years. Now there will be some models that do not deal with money, where time will not be in years, and your principal obviously would not be money. But there will be some problems, models like PERT, but where time is not in years. Okay. So here we go. We're going to do a money example. We are going to invest $12,000 with an interest rate of 9%. I want the balance after 5 years if we compound quarterly or continuously. So $12,000, what does that represent? That's what we're beginning with, and so that is our principal amount. Okay, 9%, that is what? Our rate, and are we going to write 9? So 0.09, fabulous. Okay. How many years? 5 years, so that's our time. And if we're compounded quarterly, what would our N be? Okay, quarterly means 4 times a year. So our amount is going to be the principal times 1 plus the rate over, oh, thank you, 12,000, raised to the 4 times 5 power. So if you're going to put this in your calculator, okay, you can put it like you see it, but I would make that, you can do 4 times 5 in your head, so I would raise it to the 20th power, okay? If you're not going to do 4 times 5 in your head, then you may have to put 4 times 5 in parentheses, but seriously, just do that in your head, okay? So what would our amount be after 5 years? What did you say? Okay, so let's try again. It should be like, it shouldn't be much more than 12,000, right? 18,000. Like 0.10?
Yeah.
Are we getting that?
I thought 13,020.
Okay, you know what we're going to do? Let's all put it into our calculator together. Maybe. So sorry to do that. Okay, we should have 12,000 times 1 plus 0.09 divided by 4 raised to the 20th power. So it should be 11 cents, right? All right, now, if we invest money and if the interest is compounded quarterly, that's what we get. Before we look at continuously, what should be true about our amount after 5 years compared to here? It should be higher. So our amount is principal per E to the rate times time. What do we get here? I'm assuming it's going to be around 18,000? 800 and
18,819.7%.
okay. Why would this one be a higher amount? Why is it a higher amount? Here, our interest is compounded how many times a year? 4. How often is this being compounded? All the time, okay? The more times you compound the interest, the more interest you're going to accrue, okay? The more money you're going to get out of it, okay? Now, if you're looking at a loan, would you want to be compounded more or less? Less. You don't want to pay as much money back, okay? All right, one more example, and then we'll get you to your homework, okay? You're going to see some problems like this in your book, and they're probably going to say, use the one-to-one property to solve for x, okay? How would we solve a problem like this? I have 2 to the power on one side and 8 to the power on the other side. Can we rewrite 8 as something different? What? Okay, so what you're saying is you want to rewrite 8 as 2 to a power, right? And 2 to what power is 8? 3, right? So we can rewrite 8 as 2 cubed. Okay? Which means we have 2 to the 5x equals 2 to the 3x plus 3. And how can that be helpful? Okay, if I have 2 to the power equals 2 to the power, what must be true about our powers? They should be equal, right? If our bases are the same, our power should be the same if we have equality. So 5x equals 3x plus 3. Which means x is 3/2. Okay? So if you have something to a power equals something to a power, if you can rewrite them so they both have the same base, then their powers should be the same, right? Okay, so here is your homework, okay? 19, 21, and 22. Oops. It says something about your graphing calculator. Ignore it. Those are graphs, and I want you to graph without your calculator. Okay. Make sure you're checking your odd answers, and make sure that if you need it, you remember that CalcChat is there. If you're struggling on an odd problem, you know that CalcChat will show you their work to the problem. Okay?